Good morning, everyone. Uh, thank you for coming. This is the last day. Uh, Thank you for the organization to start at 9:30 after the cocktail. So I think it's good and everyone should be fresh. We got to get some traditional Belgium weather, so you also got to experience everything. We would not want you to get some sun. So we are here today to discuss the next generation of power electronics. It's a session in two parts. We'll have 3 projects in the first part and 2 projects in the second part. So we have been talking about CCAM for vehicles, about batteries for vehicles, charging vehicles. Yesterday we had an interesting session on software-defined vehicles, and today we get to have the most important of all, the vehicles. And even more than the vehicle itself, we'll be talking about the heart of the vehicle, the power drive, the power electronic components. It's often a silent heart. We don't listen to it, we don't see it, but it's very important. You might ask, what's there to do in power electronics? We have 98% efficiency. Our power drives are very efficient, but we are looking at the next generation, smaller power electronics, more powerful power electronics, high voltage power electronics, different materials power electronics, embedded power electronics, and we need to keep pushing in this direction. We need to keep innovating, like it was said on the first day. We need to keep the edge in Europe. And the 5 projects we'll be presenting today are pushing us in this direction. So, the first project is Power Drive, and will be presented by Professor Wilmar from KU Leuven. He is also the coordinator of the research Power Electronics at Energieville. So thank you very much, Wilmar. Thank you very much for being present.
Let me see if I can find it. Yep. I will just check the time. Okay, so good morning, everyone, and thanks you all for the introduction. I think it's not showing yet. Yes. So I'm Guillermo Martinez. I am the coordinator of the Power Drive project, and as we will see, looking really into the components, power electronics components of these powertrains, with quite an emphasis in inverters and onboard chargers. Our Power Drive project is entitled Power Electronics Optimization for Next Generation Electric Vehicle Components, composed of 10 different partners distributed among 8 countries from north to south and west to east. We have 5 companies in our consortium, being Volvo, the OEM, the integrator of our technologies, SMA Magnetics, Infineon, Madworth, and Rogers, the companies, and also we have 5 academic and research institutions, Chalmers, Tampere University, Trinity College Dublin, the University of Leuven here in Belgium, and Scire in Italy. As Joao mentioned, most of the projects presented today were actually granted within this Destination 5, in the call of 2021 regarding the electronic components within powertrains. Our budget was around 6 million euros, 42 months of timeline, and we started in May 2022. So, yeah, the target indeed is power electronics within the powertrain. Our focus is more towards the inverter or the motor inverter and the onboard charger. And there we have defined quite clear goals, like for instance, 28% cost reduction, 35% loss reduction in these 2 subsystems, and quite specific targets in terms of densities, 26 kilowatt per kilogram and 50.3 kilowatt per liter in the whole powertrain. That was the general objective, but we also have some more specific objectives there. 98%, 98.5% of efficiency. Joao mentioned already that these powertrains are already quite efficient, but as we will see later in this presentation, our approach was not only to take peak efficiency, which is the one always reported by many of us, but rather actually thinking in the whole profiles, either charging or discharging profiles in the powertrain. Not only in the utilization of the powertrain, but also the charging of the batteries. Cost, of course, is quite important, another important target in this call. So we also had these targets of cost density, 12.5 euros per kilowatt in the two subsystems, the motor inverter and the onboard charger. Along with these three specific targets in terms of efficiency, power density, and cost density, we also have some other objectives. Integration is quite important in power drive. Our goal is to integrate the inverters in the motor, and also to integrate onboard chargers, possibly in batteries or also in this motor and inverter group. Simulation and modeling is quite important as well, so we are conducting the simulation and modeling of these systems and components in order to have a holistic simulation of the system, and there we have this defined this target in terms of comparing what is the information that comes from the simulation versus the actual experimentation. At least one integrated platform for testing, and Volvo, our OEM, will be in charge really of generating these data sets of measurements, integrating our inverters and onboard chargers in a demo test. So yeah, quite a lot of text regarding the objectives or the specific objectives. Here is more an illustration of how power drive is distributed. So we have, of course, the car, the powertrain in the middle, and then we have these two subsystems, which is basically the let's see if this works, yes, the traction inverter and the onboard charger, and there we have all our key technologies in both sides. Key technologies, like for instance, of course, the wide bandgap semiconductors. That's why we have Infineon in our consortium, delivering, for instance, integrated silicon carbide modules, mainly for the inverter. And in the onboard charger, we are investigating actually the use of gallium nitride. Inverters are already quite high dense, so to say. The power density is quite good. In onboard chargers is differently. We need galvanic isolation, so we need transformers, we need magnetic components. And when we actually open these devices, we see that a big portion of the volume and weight is actually used by the so-called passive components, so mainly magnetics, capacitors, and cooling systems. So, and that, because of that, we are paying attention actually to those magnetic components, cooling systems, and interconnections. And quite specifically, we are putting a lot of attention in the magnetics. So we are proposing actually the concept of controllability in these transformers in order to increase efficiency in the charging procedure. So we have these key technologies in both subsystems, but we are not only looking at those, we are also looking at the whole holistic model of these subsystems, and more than that, external effects. So we are not only focusing really in the power electronics part, but we are also thinking in what is the effect, for instance, of traffic data. What is the effect of the human behavior actually in the operation of our powertrains? And especially when we look into the whole charging profiles or discharging profiles, or load profiles, if we can mention those, that actually brings interesting conclusions and effects on the power electronics. So it's more looking at those external factors and how they affect the use of our powertrains. So in terms of specific data, power drive is intended to work in an 800-volt powertrain. So we are thinking in an 800-volt battery. And for that, again, the two subsystems, the traction inverter and the onboard charger. So here, the target specifications for the inverter, again, 800 volts. We are designing two different inverters, or thinking in two different inverters, one a 3-phase and a 6-phase inverter, and with the possibility of operating at maximum 365 amps. So there you can relate more or less the maximum power of the traction inverter. For the onboard charger, we decided to stick with the conventional 11 kilowatt onboard charger with the possibility to use gallium nitride components and evaluate what will be the effects of using gallium nitride in these components. Although in the call was not mentioned bidirectionality, we believe that bidirectionality is quite an important part for battery charging nowadays, so we integrate also the design of a bidirectional gallium nitride onboard charger in PowerDrive. So again, we have these three main targets: efficiency, power density, and cost density. And we tackle that, as we already mentioned, with key technologies. So we are integrating the inverter in the motor, the specifications I already mentioned, integrated onboard charger. We mentioned batteries and or motors. We already saw that integration of batteries is a quite big challenge. So we are actually more inclined to integrate the onboard charger actually in the very same inverter and motor case. As I already mentioned, controllable magnetics and specifically controllable transformers is one of the key innovations of PowerDrive in order to reduce the size of the onboard charger. Infineon is quite busy with the integration of silicon carbide modules, checking what are the possibilities to integrate sensors and even possibly get drivers into the whole modules. We have Rogers here in Belgium busy with the concept of interconnection, so designing low inductance bus bars, both for the traction inverter and for the onboard charger. And of course, they will generate losses, so we are doing topology optimization for the cooling part of the whole group. And out of all of these technologies, we are doing, as I already mentioned, the holistic modeling of this in order to create so-called digital twin of the whole solution. And we are building our own driving profiles. We have a certain small fleet of vehicles in Sweden, given the opportunity of Volvo, in Dublin and in Belgium and in Italy, and we are building real driving profiles for these specific conditions. I already mentioned that the part of efficiency and not only targeting peak efficiency is quite important for PowerDrive. This is actually real data measured in my own car. So not to blame any brand, let's call it a Model Y car in general. And here we can see that charging is actually never conducted at peak efficiency during different powers. It's never conducted actually at peak power, even just thinking in an 11 kilowatt onboard charger. So you can imagine how it will be actually in a fast charger, so it's even worse. But the point is that most of our designs, let's say worldwide, they are only focused on really peak efficiency, but the approach of PowerDrive is actually to look at the whole profile and try to maximize efficiency in there, and of course reduce losses and CO2 at the end. So as we are tackling different converter topologies, and as I already mentioned, magnetics are a big portion of PowerDrive in terms of innovation. Tackling efficiency, we of course reduce losses, and if we reduce losses, we also reduce, of course, the need, for instance, of cooling. So we are using less material, less copper, less aluminum. Even possibly, if we are downsizing our magnetics, we are also decreasing the use of iron, and that, as I already mentioned, is smaller cooling systems, and at the end, that will of course impact the cost savings in our powertrain. A little bit more into the dissemination. Of course, we have been also busy attending or exhibiting actually in some conferences like the CSM and ICE in Italy in 2022, 2023, here right now in RTR, and also in the TRA in Dublin in April. We will be in there. already several publications, a PhD thesis, of course, our website, social media, LinkedIn and Twitter, so please follow us. We don't have a YouTube channel yet, so I cannot say to subscribe in the red button. But we are also part of the Evolve cluster, so with the other projects that will be presented today. So we have an active discussion every other week, and yeah, discussing about the specific results of each project. Impact, of course, impact is a big and important part of the European projects and is not different for PowerDrive. So I already mentioned the results that we expect to have in PowerDrive. At the end, the main solution, of course, is an integrated powertrain, meaning the traction inverter and the onboard charger with the motor. But those final results are expected, of course, to contribute on the main outcomes is, of course, to reduce cost or to have a more affordability of these battery electric vehicles, to increase the efficiency, which is translated, of course, into range, size, and weight similarly. Easier integration in the powertrain, increased reliability. We have this holistic model of the subsystems, and because of that, we can predict maintenance and reliability information, and similarly quality levels. So far, the progress is we started in May 2022, so we are literally actually submitted our first yearly report. But we already have prototypes. We have prototypes of the inverter. We have prototypes of the curve bus bars. Infineon is busy also with the specific silicon carbide modules. And for instance, talking about the onboard chargers, we already have, for instance, results in terms of efficiency and power density. Just to mention some, 6.5, 3.8 kilowatts per liter. In these first prototypes, but of course our targets are way higher, and specifically, again, talking about efficiency, high efficiency during the whole charging profile. We have first prototype of controllable magnetics. We are investigating the hybrid pack silicon carbide module, curved bus bars, topology optimization for cooling jackets, and MATLAB models and driving profiles, as I mentioned. Again, these are the expected outcomes, but when we look further into how that will be translated, for instance, by 2030, we can see, for instance, technological impact. Of course, we expect that the results of all the projects in this call contribute to more technological standards for the next generation of battery electric vehicles, of course, and quite important to secure the leadership of Europe in this field. Societal, we know that if we maximize efficiency, of course, at the end that is translated into less losses and less CO2 generation, which is important for all of us. We know that for every megawatt hour that we save in electricity, and I really want you to remember the plot of the car where we have our charging with efficiencies of 88, 85%. So literally all the energy that we will consume in our cars should go through the chargers. So we are losing a lot there. Economical, of course, at the end, everything goes to the point of making electric mobility more affordable. And it's not only the part of electromobility, it's also the power system. So transmission system operators, distribution system operators, CPOs, charging point operators can really benefit from this. And at the end, of course, for all the academics and scientific community, all of these results can also impact them. So that's pretty much the progress of PowerDrive, what PowerDrive is, and what we intended to have in the coming years. So thank you very much for your attention.
Thank you very much, Vilmar. Okay, there is a mistake here. So now we'll have the project Rodas. And we have David Lumbreras from the University of Catalonia. He has a PhD and is a senior researcher at the MCIA Center of the Electronics and Electric Engineering Department.
Thank you, everyone. I will present the Rhodos project.
That one was on me.
Okay. Thank you. So the Rhodos project is formed by 8 partners from different countries of Europe. From Spain, we have the Polytechnic University from Catalonia, Canella and Envision. From France and Germany, we have Valeo and Valeo Automotive, the former Valeo Siemens. From Austria, we have the University of Vienna and also the Austrian Institute of Technology. From Poland, we have Bosmel. And from Denmark, we have the Aarhus University. So it's a cluster of universities, research centers, and also companies. We have a budget of almost 6 million euros. And the main objectives of this project are the ones that you can see on the screen. But just to summarize these objectives, the main objective of the Rhodos project is to build and integrate motor drive using new converter topologies and new materials. So we want to integrate an electrical motor with a power converter in a very, we want to totally integrate, making a very small powertrain with a high power density. In order to achieve that, we are working with the new wide bandgap semiconductors. We are making a power converter mixing silicon carbide and gallium nitride. And also, we want to improve other aspects of the integrated motor drive. We want to improve the efficiency. We want to reduce the size, to reduce the weight. We want to achieve a modular design in order to improve the repairability of the power converter and the system, and also we want to implement an appropriate thermal management system, as I will explain more about this later, and also a system on the cloud, a decision support system, and a digital twin in order to see if a fail is going to happen in order to act before the power converter or the motor breaks. So the main focus of the project is the power converter, but we have also to modify the motor and to design the cloud system and so on. These are the current project results. We are almost, we are at the half of the project, so we have some results now. First of all, we have defined the specifications of the power converter and also of the use case and so on. On this project, we are developing 2 power converters: a low power converter in order to test the new modulation techniques, the protection systems, the control, and so on, and a high power converter, which will be the final power converter that will be integrated with the electrical machine. Here we have an interesting problem. It's that the GaN devices, the available GaN devices, only can withstand voltage up to 600 volts. So we cannot work with really high DC boost voltage. So we are mixing, as you can see on the screen, silicon carbide and gallium nitride. We are working in a T-type power converter. So the upper and the lower transistors, which are the SiC ones, withstand the full DC boost voltage. But the transistors that are connected to the middle point of the DC boost only withstand half of the DC boost voltage. So we can use GaN in these connections. However, also the commercially available GaN transistors can withstand really low currents up to 60 amperes. So we have to parallelize several GaN transistors. We plan to parallelize 3 branches of GaN in order to work with higher currents and to take advantage of these semiconductors. Here we have some more results. In the screen, you can see the low power converter, which is already designed and manufactured. This is the first power converter that we will test, as I said before, to test the modulations, the control techniques, and so on. And we are also developing a high power converter for the final product. The low power converter is built. We have to test it in the next weeks. We plan to start the testing, and the high power converter is just being manufactured. So we are in the design process. The control system is ongoing also. And here we have another interesting problem of the project. The thermal conductivities of the GaN and SiC are really different. The silicon carbide has a really high thermal conductivity, and the gallium nitride has a really low one. It's even worse than the thermal conductivity of silicon. So extracting the heat of the GaN transistor is really challenging, and we are developing the dissipation system, the heat sinks, and the thermal interface material, and so on, in order to extract the heat for the GaN transistors. We have some simulations and we have some initial proposals. And moreover, as I said before, we are implementing some systems in the cloud. We are implementing a decision support system, a digital twin, and so on, in order to implement a predictive maintenance, and to mitigate faults, to detect faults, historical faults that the converter cannot detect, but we have the cloud, so the cloud may process these large amounts of data and detect these failures, and so on. And as my colleague said before, the Rhodos project is also part for the eVolve cluster, with several other projects in this room, like HYPE and the PowerTrain. In this cluster, we plan to join forces in order to make common publications, common research, to work together in the exploitation of the results of our respective projects, and so on. So we are part of this cluster, and we are working on it. About the long-term impact of the project, there are several points about this topic. Our plan is to, first of all, to have an impact in the new power converters. Mixing SiC and GaN devices we expect to allow to help to manufacture power converters with more higher power density, more small power converters, working at higher switching frequencies. So this has an impact on the reduction of the material used, especially at the electrical machine, since we can reduce the windings and so on. We want also to make cheaper power converters. Again, less volume is less weight, or less components in many cases, less windings, and so on. And moreover, we want to improve the efficiency of the power converter. We want to use less materials, and so on. Another interesting long-term impact here is the use of resource. T-type converters have a problem that the DC boost voltage has unbalance on the voltage. So we need to control the voltage across the two parts of the DC boost voltage, or the DC boost. So we have to develop new modulation techniques in order to control this voltage, and then we expect that future converters use these modulations and reduce the capacity of the DC boost voltage, use less capacitors, and so on. Moreover, the power converter is going to have is going to have a modular design. This allows to improve the repairability of the power converter, the recyclability, and so on. So if one part of the power converter, the integrated motor drive, fails, we can just replace this part and repair, and the product can still work. So we expect that to make a trend with this kind of design, and to then make electronics more eco-friendly, more environmental friendly. And also, this is related with the circular economy strategies, because with the combination of the modular design and this kind of design of the electronics, and with the IoT platform that we want to develop, improving the predictive maintenance and so on, we want to make a product that allow with a higher life cycle. So that's all. Thank you for your attention.
Thank you very much, David, and thank you for stepping up. The next project will be HYPE. And to present it, we have Bernard. Bernard has a PhD in electric engineering, and he currently works at Virtual Vehicle Research in Graz. So thank you very much for being, and I leave it to you.
Thank you very much, Joao. So good morning from my side as well. So the HYPE project, so not a big surprise, because all three projects were granted under the same call. So we have basically the same ideas, basically the same objectives, because we had to address the call text. So I must admit here, we are the cheapest of the three projects here. We get a funding of 5.4 million euros. Nevertheless, we have two OEMs on board. That's Ford Otosan from Turkey and Škoda. And everything we do is in strong discussion with them, because they have to have an interest and also meet their customers' expectations. So our project started in November 2022, so we are roughly a little bit more than a year, and we have a review meeting in April this year. Good. The outputs, we want to create a scalable and modular family of wideband gap-based traction inverters here. Here for the whole range of 400 volts up to 1200 volt applications. And this includes inverters, converters, and DC-DC converters. We have a family of wideband gap-based bidirectional onboard chargers envisaged based on GaN technologies. And everything should be integrated, fault-tolerant, and cost-effective. And this brings us also to the objectives. So we have to improve the efficiency of integrated wideband gap-based power electronics components and systems. So this can be done on a component level by performing a specialized cooling. I have some slides for you expressing this. This can be also done by a system approach in controlling everything in the system in a clever way, in a predictive and advanced way. Reduce the cost of power electronics components and systems is one thing, and I will show you a slide how we implement the cost assessment procedure and how do we prepare the cost here. And this is an action that is starting right from the beginning. Reduce size and weight of power electronics and electric powertrains. Reduce size and weight. This again goes with higher power densities. This again goes as a consequence with more efficient cooling technologies. We want to increase reliability and dependability through integrated design and intelligent control. But we want to increase also reliability by a special focus on digital twins here. So we are creating digital twin, as is done in all the projects. But here, a special focus is put on using the digital twin in terms of predicting if a fault might occur in the near future, yeah? And then taking some actions in the control. Yeah, and we implement wide bandgap-based power electronics, and of course, by meeting the automotive quality levels, which is then ensured by our OEM partners that we have on board. So some results. Of course, I have to go to announce here that HYPE is part of the evolve cluster, and other than my colleagues before, I want to mention that the next very important step, since we from Virtual Vehicle together with Amongo Innovate are hosting this cluster, the next important step will be a webinar that is taking place on the 15th of March. So if you scan the QR code here, you will get to a landing page and get further information for this. So what you see here is really a big number of projects that have been in the evolve cluster and are still in the evolve cluster up and running. The evolve cluster was created actually in the year 2019 with former projects from the Horizon 2020 program. And now we are in Horizon Europe, so we still have one project up and running and from H2020, and this is Multi-Mobi, which is going to be finished right soon. But nevertheless, this cluster really allows us to exchange important results or review results, of course, where it's allowed for non-disclosure purposes. You know, we have to take care about this, but it works pretty well. So we can exchange. As one of my colleagues said, we have regular exchanges on monthly meeting basis, and this is quite a good thing. Doing this, we have also made an exercise in the whole evolve cluster with the existing projects, taking the AirTruck research needs for the powertrain and looking which project addresses what. And the same exercise will be done in the near future for the Acquia 4.2.0 Strategic Research and Innovation Agenda. And then we get a good overview what we are covering with all the projects in the cluster and what is still missing. Back to the HYPE projects, we have 4 different use cases. So we have a 400-volt E-axle based on SiC inverter technologies, and we have an 800-volt E-axle also based on SiC technology. We have right bottom, we have this 800-volt gallium nitride bidirectional onboard charger technology, and on the left side you see inverters that are used for chassis actuators. So here we are going to address the performance needs for the vehicles. So chassis actuators, as you know, have an impact on the performance, and performance itself has an impact to sell the vehicles, to sell the technologies, and this should be covered here. For the cost assessment procedure, yes, we have developed and we are currently accommodating a procedure how to assess the cost assessment on a total cost of ownership base, meaning that we do not only have to reduce the cost for the different components, but the different components have also some features. Yeah? And the features have an impact of the overall efficiency of the system, of the vehicles, and this results again in a cost benefit. procedure, we are right in the middle. We are currently about creating adapting tool according to the defined methodology, and the first results we will have on the table roughly in 1.5 years. What have we done so far during the first year? We took great care on, together with our OEM partners, in defining the requirements and specification of what we do. Requirements and specification in terms of hardware, in terms of inverter, in terms of system, in terms of control technology, and in terms of simulation efforts, and how a digital twin could operate. And for the digital twin, that's worth mentioning, digital twin is not running somewhere in a cloud or on a big computing system. It should run in the car itself. So this means we need to have for the digital twin some kind of model order reduction technique, and this is very important to put them on the controls we have in the vehicles. Simply, you can imagine it's not feasible when I want to control some fault-tolerant system. It's not feasible to do the communication via the cloud and back. I have to have it in the car. Yeah, we have the vehicle requirements. We have the mechanical, electrical, and electronic interfaces, data communication protocols defined, a testing platform, because we want to evaluate our results at the end. Of course, the testing platform, interfaces and specifications are defined. The simulation requirements and specification for this are defined. So some words, a little bit deep diving into some technology results. So semiconductor cooling, as I mentioned, a very important point here, because when we want to reduce size, power density is increased, and therefore we need efficient cooling techniques. So here we have a design for the cooling pins for a semiconductor, and this optimization is done. We have developed and built up a prototype, and the prototype has been tested also in reality in one of our labs. And I can tell you, it's not an easy thing to measure the temperature distribution and the heat dissipation of a semiconductor. So you have to take special care about the instrumentation. But nevertheless, we got a result which is pretty close to the simulation. So that gives us the confidence that we can use this approach also for creating digital twins here. So mid to long-term expected impact on a very high level, of course, the accelerated uptake of zero tailpipe emission, affordable user-centric solutions. This is done here in Advise because we have efficient powertrain. We take care of also performance of the vehicles, as I mentioned before. We have very close look on the total cost of ownership perspective of the vehicles, and this should help us take this vehicle, uptake this vehicle into the market sooner as expected. Increased user acceptance, again here the performance, the price, the cost, and especially also the issue that everything is controlled in a proper menu, in a proper way, such that also particle emissions can be avoided, and from tire wear, brake wear, and so on. This has, of course, an impact how you control your drive, and how you control your drive is again a result of how you control your inverters, and this is a matter of how well your digital twin is working. Effective design, assessment, deployment of innovative concepts. The simulation, as my colleagues before mentioned in their projects, simulation is quite important because we need simulation not only for creating digital twins, but we use the simulation also to create modular approaches for our power electronics. Modular approaches means, as you mentioned before, that we can exchange faulty elements in an easy way, and it still works. Yeah, that was a quick guidance through the HYPE project. So I'm pretty sure I will be here next year to give you more information about innovations that we developed. And thank you very much for your attention.
So thank you very much, Bernard Brandstatter. No.
Say Bernard.
So now we'll start the question session, and we have my co-moderator Roland Ulrich from Aachen University. So please, if you have any questions, let us know.
Yeah, so also from my side, a big thank you for the nice presentations. Sadly, we cannot fast forward to next year and have all the results shown. But nevertheless, now you have the chance to ask your questions, and maybe some early questions also have come up this year. So looking forward to your questions. Otherwise, we have some, I guess.
Thank you. Thanks again. Just to break the ice and to start with a simple question, something I was wondering, because I saw that for Rose you were working on solution ready also for the 1200 volt. And I was wondering, the other project as well are working that way? And do you think that this will be the standard in the future? Oh.
Since I had a very similar question on other things, maybe we group everything, because it's, the first project highlighted two things which I think is important, and I commend for saying this is needed and we put it in, which is two-way. And also they stressed and presented the material on the losses for the charger at lower. So I would like to know what the other projects are doing.
And I'd like to start here. So for coming back to Guido's question, yeah, we of course are considering on a simulation basis what can be done for the 1200 volts, yeah. But we do not have a demonstration in this way. But of course we are considering this, and this will be done on a simulation basis, yeah, in HYPE. We are aware, very aware, that 1,200 volt is a very relevant step, yeah, and we are therefore looking at it. In terms of losses, yeah, for all the mission profiles we are considering, yeah, we do this via our digital twins. In the HYPE project, so we are assessing our simulation, of course, really creating digital twins, also in terms of taking measurements from the real built devices, yeah, to tune our models, and then we extrapolate what happens during the mission profile. Yeah.
I was referring more on the stress they made on charging at lower than design power, because this is particularly important just for not throwing away 20-30% of the energy, but also since they consider V2G, if you have the loss 2 times, it's even more important.
Yeah, clear. Yeah. Yeah, so we are looking at it, but there is no special task for it. But we are definitely looking at it. And this will be reported.
It's a not easy task. Huh? It's because we need to look really into all the technologies, starting from, of course, from semiconductors, linking, of course, to the 1200 volt discussion. Of course, going up in voltage will help in terms of at least all of these copper losses or eddy losses in also there in magnetics helps. But technology, at least for gallium nitride components, also 1700 silicon carbide devices, integrated ones, it's difficult. And also when we look into the topologies, I mentioned it, that's the target, but levelizing all of that efficiencies at light loads is certainly not an easy task, but is indeed key if we want to reduce energy consumption in electromobility.
Horst Flügel-Eviel. What I think you all spoke about reliability, lifetime, and prediction. What is the expected lifetime? And especially if you look at bidirectional charging, where we need some longer lifetime, what's your considerations there?
Also difficult one, huh? Good thing is that, of course, when we talk about B2G or bidirectionality, at least for the internal components inside the car, battery also, these charging profiles, we are talking about different power levels. So if we have towards the motor drive, the inverter, we are talking in the range of hundreds of kilowatts. When we talk in V2G, we are talking about in tens, even several kilowatts. So in terms of reliability is less impactful, so to say, to the devices when we are going to use the battery to charge or to power our home or to power another car. It's an open question, so I think the projects were still quite young in that sense to come with dates or with a number of years in terms of bidirectionality or even in the other components. But certainly it's there in the planning, and perhaps will be one of those last tasks to report reliability and also cost. Yeah. But we foresee that it's less impactful as, for instance, the traction inverter.
Maybe.
Yeah, if I may add here, reliability is, I think, in all of our projects covered by this digital twin approach. Yeah, and we want to predict if a fault occurs. So that's a less difficult thing than predicting the lifetime. You know, because the lifetime, especially for bidirectional charging and so on, depends very much on the pulses you use. You can charge also with pulses and the signal quality itself plays a very important role, which is not yet analyzed and still under investigation. I don't think that we have a clear picture how to charge a battery with which signal at the moment. Yeah.
Okay, maybe just a quick follow-up to that situation, because you mentioned the battery already. When you now set that into context, so the durability and the lifetime of the charger compared to the battery cost and the lifetime of that component, in your opinion, is it really relevant to have such a close look at the durability of the charger in comparison to what the battery faces during the lifetime?
Well, I can only give a personal opinion here, and I really think that is extremely relevant what the charger is doing with the battery, because when some cell voltage is measured in the wrong way, yeah, or slightly different, you can undercharge the battery or overcharge the battery, and this affects, of course, the lifetime. So what you're doing with the electronics to the battery is, of course, relevant.
We had one question in the front first, and then.
Yeah, I'm asking more or less the same question that I asked last year to the projects. Of course, the call was designed like this, and this was the target of the call. But I see a focus on high voltages, 800, 1200, even more. No? Of course, maybe it was not part of the core of the project, because it's the project was concentrated only on the power electronics, and this is the focus. But did you make in terms of reliability, just linking to the question of Horst, did you consider the aspects of the reliability on the battery pack? The battery packs are made of lithium-ion cells, which, if there is anything new, I don't see. Maybe the battery projects may say something, but more or less, the voltage of each cell is in the order of 3 volts or so. So to reach 800 volt, you can divide 800 by 3, and the series of cells is quite long. So, did you make an estimation of the reliability of those longer series of cells having such a high voltage, or did you consider different topologies like DC-DC converter or so, which, by the way, from the point of view of the efficiency, they are not so good.
Okay, thank you for your question. In the Rhodos project, the battery is not included in the project, but of course, this is a problem that we have to have in mind. Commercial batteries, I think that can give a voltage up to 600 volts, more or less, but there is a trend on increasing the voltage of the batteries. So on our project, we are not taking into account what you say, the reliability of the battery and so on. But we have the problem that the power converter needs to work with high voltage, and the battery may not give this voltage. So in most cases, there is a DC-DC converter between the battery pack and also the power converter that just raise the voltage. But in particular, in our project, we decide to avoid this DC converter, since the trend is to increase the voltage of the batteries, and also most of the functions of that this DC converter performs can be performed by the AC by the DC AC converter. So avoiding this power converter will allow us to make cheaper IMDs, and also with less components and more compact and so on. So the short answer is that no, we don't have we don't have taken into account what you said. But thank you for your question, because it's really interesting.
We trust in the battery management system. That will be.
Not the battery management, yes.
Well, the BMS, because at the end, and it's actually quite relevant. I talk a lot about battery charging, and the BMS is really limiting the performance of the whole system, actually, also for a traction inverter. It dedicated a whole big portion of the projects if we had been looking into the battery. So we assume really the battery as a given, and that the battery management system is doing the work. I think similar as the colleagues here, we choose high voltage following the trend. Also because thinking in reliability, it will mean actually lower currents flowing through the battery, which at the end impacts in a good way the lifetime of the battery.
Yeah, similar to the other projects, and not considered in HYPE in the project itself, but of course on a simulation basis we have models for the battery cells and include them in the loop somewhere. Yeah.
Yeah, we had two questions in the middle, or I think Eric was first. And
Thank you very much. So, Erika Mango, AIG. So, I will have the pleasure to present IceCap project related to these topics on the next session. And I invite you to so reflect or to mirror my question I will ask you right now for the next session. So, here we see that power electronics is very on the core of the vehicle and having strong dependencies to other aspects. And I wanted to ask the topics of open innovation so in terms of ecosystem. So here we are speaking about new devices. We are speaking about truck manufacturer, car manufacturer. We are speaking about component powertrain system. We are speaking about interaction with the battery, with the e-motor. So here, how is your feedback? What is your experience in terms of having a very focused activity on power electronic and having so much interfaces, and how do you manage the onboarding of the full ecosystem to an appropriate level? So how far to address battery topic, how far to address evolution in the semiconductor aspect, how to address the car and truck manufacturer, so ecosystem, open innovation, ecosystem management. So what is your lessons learned?
Thank you for this very difficult question. Yeah. Well, that's really a challenge and a hard topic. As you know, we have all or most of us have some experience in placing components into systems, evaluating them first via simulation, then on test benches and so on. Digital twin is one thing that comes up right now. But the devil is always stuck in details. So this might sound very, very simple, but it's really a challenge. Yeah, and of course, when we speak about modularity, we want to exchange the components, we want to exchange subsystems, and this is a matter of how do you describe your models and your subsystems? How do you describe them in a way that the interfaces are clear, the system boundaries are clearly defined, such that somebody else can use them? Yeah? And this is quite something where we possibly are just about to start thinking. Just then.
Okay, I hope that answers the difficult question for the early stage of the project. So we had. Oh, sorry. Okay, sorry.
So you have the answer.
Julian Stoev, Blue Ways. I'm hearing here a lot of digital twin talk. Okay, this is quite common, but now I heard something about using it in the car. And yes, of course, you talk about model order reduction and things like this, but still, do you think, how do you expect the computational demands will go in the car, I mean, not on Amazon Web Services?
Yeah, since I brought this up, I tried to answer the question. So I also talked when I talked about digital twinning. So digital twinning doesn't mean for us a simulation only. We need to get the data, the real world data from different measurement points in the vehicle to adopt also our simulation tools and the digital twin, because the digital twin has to be anytime a representative of its real world twin, yeah, counterpart. So how do we calculate this in the vehicle? Yeah, of course we are using model order reduction techniques. So it could be radial basis functions, this could be artificial intelligence, this could be a neural network in a trained way to get very fast the answers. Yeah. We are not talking about deep learning. We are talking about model order reduction here. Yeah.
Okay. So actually, these are rather simple models which will not require a lot of computational.
Exactly. Yeah.
Okay.
Okay, I think there was one back, and then Simon and Ian had questions as well.
Hi. My name is Ciro Attaglianese from Electrification and Mobility Consortium. I have a question. Did you investigate also new topology, especially for the onboard charging? Because in some countries like USA and Canada, they are using PPP, partial power processing converter, which are promising for increased efficiency, especially at low load. They have the problem of galvanic connection with the galvanic insulation with the network, but in this country they are revising the standard on this topic. So I'd like to know if topology is fixed, classical, or are you investigating new ones? Thank you.
Yeah, maybe I can start. Yeah, certainly that's a big portion of at least. Assume the same for all the projects. We don't fix the topologies, and we play what we can basically in there. I mentioned a lot, for instance, regarding the magnetics. We believe that, of course, simple is better in terms of power electronics and less components. In a world where we are talking more and more about sustainability is also quite important. So tackling in a smart way some other, like for instance magnetics or cooling devices could also play a good role there. So yeah, we are looking indeed into topologies.
In the case of the Rhodos project, the topology was already fixed, but we studied all the topologies at the beginning of the project in order to see if we can improve the topology and so on. But we stand with the T-type converter topology because of the GaN transistors. The GaN transistors are really fragile. So if we have a fail, this is a kind of topology that allows us that if we have a fail, if we detect a fail of the GaN transistors, or if a GaN transistor fails and remains on open circuit, we can develop, we are already developing algorithms to work only with the SiC transistors. So it is an extra layer of reliability that we want to implement on the power converter.
Yeah, for the HYPE project. For the HYPE project, the bidirectional onboard charger has not a fixed topology. We are working on this, and the first step is, of course, again on a simulation basis, but it's too early to give you some results how this would then behave in reality. So this is under investigation currently. Marco.
I guess Ian had a question first, so and Simon Edwards after that.
This is Ian Fire from Bosch. I do have a question, and I would like to get an answer from each of you, and it's a bit on a global galactic level, as I always promise. Our ambition with funding is to achieve, say, European competitiveness, achieve the Green Deal goals. But in this case, I would say probably that one of the big bets here is how do we achieve technology leadership? And the world of power electronics is of course very dynamic. It's moving big steps, leaps and bounds. So how are you doing benchmarking? Are you watching what's going on outside, say outside of within Europe, outside of Europe, worldwide in terms of power electronics and your concept? So are we achieving our technology leadership with these projects? And if we don't have an answer today, then I hope to get an answer at the next RTR or as soon as possible. So what are you doing in terms of benchmarking?
Thank you, Ian, for the question. For the global galactic question, I will answer first in a global galactic way. Yeah. What the benefit of our cluster is definitely that we can exchange our findings when we scout what's happening outside Europe. Yeah, we by having made this cluster, we are pretty sure that we can monitor and scout what's happening outside and what we do in our projects in a much more effective way than we were just single projects.
Of course, it's goes to many levels. When we look into media, and it's basically everything only to the vehicle manufacturers and all the threats that are outside of Europe. But of course, in a more power electronics related call, we look really into the components. So are we really the leaders in Europe in certain things? I would say yes. For instance, looking into semiconductor technology, I think we are quite well positioned in silicon carbide, for instance. We have also the so-called GaN, gallium nitride valley here in Belgium, although Belgium is not a valley in its own. Looking, for instance, in some other technologies like for components, passive components, gets more tricky when we go, for instance, in terms of access to raw materials like copper, iron, aluminum. So it's quite a big point to evaluate when we look into all value chain there, going from systems until the very same materials. Are we doing well in some certain topics? Yes. In some others, we need to go and do better.
Okay, in my opinion, what this project serves to, we are in the good way to taking leadership, as Wilmar said, in the components part. From my experience, there are few people that are working with wide bandgap power converters, and especially few people that are working with gallium nitride, especially at high power levels. There are tons of investigation of gallium nitride, of silicon carbide, especially of silicon carbide for automotive projects. There are tons of it. There are gallium nitride and low voltage applications. But most research teams and so on do not operate these semiconductors at high powers or at high switching frequencies, which is, I think that's the point of using these semiconductors, because if we are not taking advantages of these properties, why are we using these semiconductors? We can just stand with silicon and continue our lives and so on. But there are few people that is working on these research on these research topics. As far as I know, some teams from the UK and also for Singapore and so on. But there is really few teams that are working on this topic. So I think that the European Union, and particularly this project, are in the good way to achieving the leadership on the how to use these components and how to take advantage of these properties.
Thank you. If I may then, Roland. Yeah. So just Simon Edwards, Ricardo, thank you very much to all the presenters. That's very good, a good broad view. And this is really a bit of a request following the same thoughts as Eric and of Ian. And as I guess then it goes towards the cluster leader in the first instance, really. You've done some good illustration there of the mapping of the projects against the applications. Really, I would like to see that go further and understand the expression of the targets against the mapping against the projects, then the baselines, and then the results, please. And I know I've got a self-interest for asking this question, and I don't need an answer right now, but just please bear it in mind when you work through all of the projects with your cluster results. Thank you. Ben.
Yeah, thank you, Simon. You rush into open doors, so I think Eric and me are really going in this direction, but we have to go it step by step. Yeah.
Well, I think there was some I don't remember which of the presentation highlighted this aspect, and perhaps it was in any case part of the let's say side request of the call, recyclability. And in particular, recyclability of power electronics. We all know how the problem of the recyclability of consumer electronics is becoming a problem, but the problem will be even bigger because the amount of let's say material in a power switch is much higher than what it is in a cellular phone or so. And in particular, considering these exotic material like silicon carbide, gallium nitride, and so. I ask this because I see that at least in 2 of the 3 projects, you have also semiconductor manufacturers inside, Infineon and Nexperia. Unfortunately, we don't have the 3rd one in Europe, which is STMicroelectronics, but hopefully maybe in some of the other projects will be. Did you make some consideration on these aspects? Are you planning to do something like this?
From the Rudolph project, some manufacturers are not partners of the project, but they are on the industrial advisory board of the project. So we have contact with some of them, particularly with Infineon and with GaN Systems, which are not the same company, but that's another topic. Recycle the power electronics is really tricky. So the prisma of our project, it's not recycle the components, it's out of our hands, but just to improve the reusability and also the repairability of the power converter and also for the AMT. That's why we are aiming for a modular design and so on, just to exchange, if one module fails, change one module for the other and then repair the broken parts. And also we are developing an eco-design guide just to improve this aspect. We have to know if when we broke a PCB, we should test the components, which component is okay and so on, because we can reuse these components and in most times these components are just not reused again and are totally functional components. So we are not aiming for the recyclability, but we are aiming for the recircularity, the repairability, and so on.
Yeah, we have of course Infineon in our consortium, and it's difficult to think in how to recycle power electronics components when it's such a complex systems, only looking, for instance, into all the processes that silicon carbide have, the packaging and the use afterwards. What we are trying to ensure is that we can maximize the lifetime of such devices so that we can at least meet the lifetime of other components, like, for instance, batteries that we were discussing before. But it's still a quite fuzzy and open questions. Like, for instance, we don't know even how to recycle in a proper way many things. Even we don't know what is the CO2 footprint of a PCB circuit and so on. So it's a lot. So within one project, it's certainly difficult to meet everything. So. Yeah, please keep funding us. So that's.
Why are you looking at me?
Yeah, for HYPE, we are looking at on the same level. We have the same vision where we try to make a modular approach, exchange components, and not to throw away everything, but only things that really have a failure. But since we have Nexperia on board, and it's not recyclability is not a target in this project. Yeah? But since we have Nexperia on board, we have it every time in each general assembly the point recyclability brought up by Nexperia. So I think I'm pretty sure they are aware of it, and because they have to address this because it's their business.
Okay, we still have time for one or two additional questions. Otherwise, I think we have one from your side as well.
Okay, I can ask one very short to each one. So, to power drive, so you have the integrated power electronics and the motor. What happens if you need to update it, if it fails? What do you need to replace? And how does this affect the total cost of ownership? To RODAS, you propose a hybrid system, so 2 gallium nitrate and 1 silicon carbide. Again, when one of them fails, do I get change the oil type of warning, or do I get red engine type of warning on the car? Can the car still run when one of them fails? And finally, IP, Bernard, you mentioned a lot digital twins. Yesterday, we also had the plenary session on software-defined vehicles. So these digital twins, are they going to be what the car manufacturers are going to make money on when you change a component, when you need to update it? So, thank you.
Okay, yeah, we indeed having the target of a high power density in the call or way to go was, and also of course one of the expected outcomes was the integration indeed. So we have the target of having the motor drive and possibly also the onboard charger integrated in the motor case, and that's why we have this round structure there, and with that we achieve actually high power densities. That give us also the opportunity to have some possibilities of redundancy and to some extent modularity, thinking for instance again in the fact that we will not work always at high power levels, that we need to also work at light loads. So modularity is one way to go to use a few of those. So will they still run if some of those fail? Yes, because we have those facts. The part of the modeling and simulation help us also to predict when that can happen, so that we can at least do predictive maintenance and approach that. Specific results about that, of course, that will come later. So hopefully in the next one we can have a more clear answer to that one.
Yeah. About the modularity of the product project and the hybrid design, depending on which type of failure happens and depending on which component happens, the system may break totally, or we can replace them. That will depend on the type of failure and also on the final design of the high power converter, which is not totally close. Our idea is to make the most reliable system possible. So if one of the GaN fails, as I said, we are parallelizing several GaN transistors. So if one of the GaN fails, we may use the other GaN transistors and working with low current and also with low speeds and power of the electrical motor. But yes, we are working for ways to not throw away the power converter or the whole EIMD in case of a failure, and I think that we are in the good way. But this is a topic that we are now developing, so I don't have a closed answer on this. And yes, about the digital twin, we want also to implement a digital twin to predict the failures and so on as the other projects. And I think, it's my personal opinion, that this is a tool that car manufacturers may used in the near future to detect the failures in the cars and the trucks, and to send the user a message saying that there is a possible fault or a revision and so on. And I think it's a really good way in order to save futile maintenance operations and to optimize this aspect of the electric mobility.
Yes, indeed. And in terms of digital twinning, digital twins are really the kernel of everything that we plan in the future, especially software-defined vehicles. And digital twins enable, of course, this fault-tolerant control of what is existing in the vehicle. On the other side, digital twins will be used for virtual validation of what comes into the vehicle from outside. And here especially, there is one other thing I do not know, since I have not been here yesterday while Max Lemke was, I think, having the keynote on this. One of the major topics here for software-defined vehicles is also the hardware abstraction layer, and how the hardware abstraction layer handles the digital twins that are of course the input. What happens for software updates here, and in my opinion, yes, I think it is in the responsibility of component providers and system providers to provide also the digital twins, or at least we should create some methodology, some standards on how digital twins are created, what kind of standards are used here to create these digital twins, because this is really an essential part, in my opinion, my personal feeling, because we have to take care that this particular key element, the digital twin of everything, really works in a proper way for everybody.
Okay, thank you. I guess we have one final question from the audience.
Hello everybody, I'm Lucian, I'm from Dell Technologies, and I have a really quick questions for all of you. What is the test related as a lifetime of each component that you are building and testing, if there are any tests? Because I'm thinking also as a client perspective, as a final use, if I'm using something as a new technology, what is the current lifetime of that particular component?
Yeah, let me give a very general answer to this. Usually what you do is, when you have a new component, you make a stress test, create Arrhenius function to predict what's happening in the future. And to define these stress tests is different, of course, for the different components. Yeah, what you're using. It's different when you're creating an electrical machine, and it's different when you're using considering an inverter. But basically, a central thing is, these stress tests involve mechanical stresses, involve temperature stresses, and also electromagnetic stresses.
It goes to many levels. In power electronics components, in automotive, we have a tremendous amount of many components. We go again from semiconductors to passive components, and again, as Bernard mentioned, we try to build mission profiles for at least converter level, and that converter level also will bring mission profiles to components. Of course, we want all of those to be in the 20-year time frame, but only looking, for instance, at a single one, electrolytic capacitors, for instance. Those are extremely tricky to build and to check, sorry. And depending on the mission profiles, if we have, for instance, certain rise in temperature, lifetime will be drastically affected. So it's a long list in the bill of materials, choose the most sensitive one and start building mission profiles for those. Check what will be the harsh conditions. Of course, we want all of our cars, and especially electric, as fast as we can. So really high current profiles for all the components. What will be at the end the effect on lifetime of those? But yeah, decades, of course, we want in all of the components.
Yes, as my colleague says, this is a really complex question and will depend on the mission profiles and so on. So I will not repeat what they said. But I will say that that's one of the things, one of the advantages of implementing a digital twin is to predict this lifetime at least to see if one component is more probably to fail than others. Because if we detect in the digital twin or in the cloud system and so on that the mission profiles are really hard or really tall, we can expect an early failure of certain components. So this tool may help us to predict when one component will fail, or at least to have a general idea.
Okay, I guess we have run out of time already. So if there are no urgent questions or otherwise, you have to ask them during the coffee break. So looking very much forward to seeing you with results next year. And till then, a big thank you for your endurance during this Q&A session.
Please join us at the next second part of this session at 11:30.